Top Secret Psi-Operative Training Mission. Reading Passage Ionization Energy. Mission: Understand ionization energy and how it impacts reactivity of elements. Tips: Remember to beam as you read through the passage below.
Hi, Dr. Pauling. I'm trying to upgrade my armor and laser, but notice that they are restricted to a few elements. Can you help me understand why?
I would be happy to help you understand your gear better, Aki. Let's talk about your armor first. The best elements to use for your armor are stable metals. Metals are great choices for armor because they are usually solid at room temperature and are malleable, so they can be custom shaped to fit your body well. They also conduct heat away, helping you cool off quickly if you do get blasted by the hive in battle. Non-metals and metalloids tend to be brittle, so they would break too easily if they were armor. Remember that a lot of non-metals are also gases, so they won't work for armor anyways.
You said stable metals are the best for armor. How can I tell if a metal is a stable one?
It's actually easiest to identify metals that are reactive or less stable. This is because reactivity of metals is associated with something called the ionization energy of an element. Ionization energy, i.e., describes the amount of energy required to remove a valence electron from an atom. Metals that have low ionization energy values are very reactive. Metals react by giving out electrons, so if they can lose their electrons easily, then they can react very fast. If you look at the ionization energy values on the periodic table below, you can see that the metals we use for armor generally have higher ionization energy values than those that we don't use for armor. Scandium, symbol capital S lowercase c, for example, has an ionization energy of 633 kilojoules per mole, and makes great armor. But calcium, symbol capital C lowercase a, right next to it, is very reactive with an ionization energy of 590 kilojoules per mole. Metals like calcium are too unstable to use as armor because they would react with elements in the air and even with water.
The diagram at the bottom of page 1 shows the ionization energy for the majority of elements on the periodic table. Ionization energy is in the units of kilojoules per mole. The numbers under each element symbol are the ionization energy values. Elements that are metals are in light yellow, armor metals are in medium yellow, metalloids are shown in orange, and nonmetals are shown in dark red.
So, if I'm reading this right, the ionization energy gets smaller going down a group and gets bigger moving across a period. What is causing that?
Diagrams like these are very useful to scientists to quickly interpret properties of elements, and you did identify the general trend. This trend exists due to the effective nuclear charge, Zeph, which is the overall attractive force felt by valence electrons. As you look at representative elements across a period from left to right, the Zeph increases because protons are added to the nucleus. A stronger nuclear force helps hold on to these electrons more tightly and makes them harder to remove. For example, let's compare the Bohr models of strontium, symbol capital S lowercase r, which is too reactive to use for our armor, and indium, symbol capital I lowercase n, which we can use for armor. Their valence electrons are approximately the same distance from the nucleus in the fifth energy level, but indium has more protons in the nucleus than strontium. This means the Zeph will be stronger for In than Sr, making it harder to remove those valence electrons from indium atoms.
Indium has a lot more protons than strontium, though, so why isn't the ionization energy a lot bigger?
That is actually because of extra electron shielding by indium's 10-4d electrons in the n equals 4 energy level. Electron shielding is the idea that electrons in energy levels closer to the nucleus block some of the nuclear force felt by valence electrons. This effectively reduces the Zeph on the valence electrons, so even though there are a lot more protons, the valence electrons only feel a little bit more force, and the ionization energy only increases a little bit. This is also why there are not big differences in ionization energy values for the transition metals, since they all have electrons added to d sublevels.
Is this also why the ionization energy gets smaller further down on the periodic table? I know those elements have a lot of electrons.
Good hypothesis, Aki. The main factor that makes the ionization energy smaller moving down the periodic table is the increase in distance as more energy levels are added. You can see this in the graphic to the left. However, the electron shielding does add to the effects that we see in the trend.
Okay, I'm starting to get this. Increasing protons in the nucleus has the biggest impact when you go across the periodic table. This isn't the same as you go down, since increasing the distance from the nucleus best explains the trends we see. Electron shielding explains why the numbers don't change more, because it usually decreases ionization energy.
You've got it, Aki.
This helps me understand what's happening with the stability of my armor. But now I am wondering about my laser. Most nonmetals have really big ionization energies. Does that mean they are already stable?
Some are, but not all nonmetals are stable. The noble gases in group 18, like neon, symbol capital N lowercase e, have a full valence energy level, making them very stable. The halogens in group 17 have an almost full valence energy level, which actually makes them very reactive. This is why we do not use halogens in our lasers. Since they are very close to being like noble gases, they have a very strong hold on their electrons and have very high ionization energy values.
The laser shown in this diagram is equipped with the noble gas, neon, symbol capital N lowercase e. In the Bohr model on the left side, you can see 8 valence electrons in the second energy level of neon, giving it a full outer energy level. This makes neon very stable and a great choice for usage in a laser.
But wouldn't using more reactive gases give us more energy in the laser? I'm thinking that something like fluorine would be a good option.
Whoa there! I see what you're thinking, but that would be extremely dangerous. The halogens are so reactive, they will try to react with anything. Just coming into contact with your laser gas container could cause your laser to explode.
Okay, stability is key. Looking at the ionization energy values, I see some numbers that look like they are wrong. If ionization energy always increases from left to right across a period, why is the value for beryllium, symbol capital B lowercase e, higher than boron, symbol capital B?
There are exceptions to the general trend. We can see why beryllium, symbol capital B lowercase e, has a higher ionization energy than boron, symbol capital B, if we look at the electron configuration. Elements get a stability boost when they have half-full or totally full sublevels. Beryllium has a full 2s sublevel, but boron only has one electron in the 2p sublevel. This means it is easier to remove the one electron from boron's 2p sublevel than it is to remove any electron from beryllium's 2s sublevel. If you look closely, you will see that same pattern in every period. Magnesium, symbol capital M lowercase g, for example, has a higher ionization energy than aluminum, symbol capital A lowercase l, for the same reason.
I think I see another exception. Most of the elements in group 15 have bigger values than group 16, which doesn't follow the same trend as the other groups.
Nice spotting, Aki. The reason for this is similar to what is happening with beryllium and boron. Elements in group 15 all have 3 electrons in a p sublevel. Since the p sublevel holds 6 electrons, the elements in this group get a stability boost from having a half-full p sublevel.
Why do they get more stability from being half full? That seems kind of random.
It all comes down to symmetry. When the sublevels are half full or totally full, the electrons are symmetrically placed around the atom. This symmetry leads to the ideal distribution of charges. Also remember Hund's rule. Electrons are more stable when they do not share the same orbital. Since a single orbital can hold two electrons, having one electron per orbital really minimizes repulsive forces between negatively charged electrons.
The diagram shows the orbitals in the second energy level of nitrogen, symbol capital N, and oxygen, symbol capital O. The valence electrons for both nitrogen and oxygen are found in the 2s and 2p sublevels, with oxygen having 4 valence electrons in 2p, while nitrogen only has 3. Since p sublevels contain 3 orbitals, the 3 2p valence electrons in the electron configuration of nitrogen, symbol capital N, spread out symmetrically around the atom with 1 electron in each orbital. Since oxygen, symbol capital O, has a fourth 2p valence electron, 1p orbital now has 2 electrons, which increases repulsions and decreases stability.
I guess that all makes sense, but I still see a few elements that I don't understand why we can't use them as armor. Beryllium, symbol capital B lowercase e, and magnesium, symbol capital M lowercase g, have pretty high ionization energy values, even higher than some of the elements we use for our armor. So why can't they be used for armor?
That's actually a really good question, Aki. Beryllium and magnesium are both much smaller than the elements we use for armor. This smaller size means that the nucleus pulls more strongly on the valence electrons, making them harder to remove, which is why the value is higher. However, elements with full sublevels are the most stable, and beryllium and magnesium can achieve this if they lose their 2 valence electrons. Losing these valence electrons makes beryllium and magnesium isoelectronic, or having the same electron configuration as a noble gas with full s and p sublevels. So even though the ionization energy is higher, these particular elements become a lot more stable if they lose their valence electrons.
We can see how elements become isoelectronic in the diagram. Beryllium, symbol capital B lowercase e, has an ionization energy of 899 kilojoules per mole and has an electron configuration of 1s2, 2s2. When Be loses 2 electrons, it now has an electron configuration of 1s2, since it loses the 2s electrons and is now isoelectronic to the noble gas helium. This also gives Be a +2 charge because it lost 2 negative electrons. Magnesium, symbol capital M lowercase g, has an ionization energy of 738 kilojoules per mole and has an electron configuration of 1s2, 2s2, 2p6, 3s2. When Mg loses 2 electrons, it has a +2 charge, has an electron configuration of 1s2, 2s2, 2p6, and is isoelectronic to the noble gas neon.
This has been really helpful. Thanks for helping me avoid armor that breaks down and a laser that explodes.
Make connections. In each box below, write a connection between the text that you just read and either your prior knowledge or something in your life. Reading comprehension questions. Ionization energy. 1. Define ionization energy. 2. Which of the following diagrams correctly represents all of the general trends on the periodic table for ionization energy? Circle the correct choice. 3. Define Zeph and explain how it contributes to changes in ionization energy. 4. The diagram on the first page of the reading passage is missing the element astatine, symbol capital A, lowercase t, which would be located at the bottom of group 17. Predict an ionization energy value for astatine and explain the reasoning you use to determine that value. 5. Summarize how electron configuration helps explain exceptions to the general trends in ionization energy. 6. Compare the Bohr models and electron configurations of Cu and Zn to answer the following questions. The Bohr model of copper, symbol capital C lowercase u, is shown on the left side of the diagram. Copper has an ionization energy, or IE, of 749 kilojoules per mole. It has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. The Bohr model of zinc, symbol capital Z, lowercase n, is shown on the right side of the diagram. Zinc has an ionization energy, or IE, of 906 kilojoules per mole. It has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. A. In what energy level and sublevel are the valence electrons located in Cu and Zn? B. Would Cu or Zn have more electron shielding? Explain. C. Explain why Zn's IE value is so much higher than Cu.